Okay. Hey, where was the other speaker who joined us earlier?
Maybe we can wait 1 more minute.
Sure. Okay. Okay, I think we should get started.
Yeah.
Okay, good morning, afternoon, evening, or even night to everyone. So let's start this session. And before we get to our invited speaker, we can there are some announcements. So just firstly, this is a Zoom link, and please join our Slack channel. If you haven't joined it, give me a message. I can bring you in. And there's a Slack channel for this specific SIP, which is called 2022 SIP on the -ML. And in this channel, you will see all the information you need, including the Zoom link, even a gather town for a small chat. And for all the speaker, if you it's not required, but if you are okay, please upload your slides after your talk. Also, our workshop is also on live stream on YouTube. So this is also the button you can click to get there. So if you have any question, leave a message in the Slack channel. So under the thread for each talk, so that we can better track the questions. But if you do have questions and you are and you want to just interrupt and ask the speaker, I'm sure we will be fine. So just unmute yourself and ask the question. All right. And I think I'm also supposed to.
You're muting, Yushan.
So I have been muted from the beginning, or just.
No, just the last part.
Just SAZERAC meeting. Okay, so just a quick reminder, please register for this next SAZERAC meeting. This is specifically targeting on 21 centimeter. It's supposed to be a bigger event, so please take a look. And with no further delay, let's start with our invited speaker, Professor Catherine Chok from Curtin University.
Thank you, Yushan.
Catherine, so yeah, all good.
Yeah. Okay. All right. Can you still hear me?
Yeah.
Yes.
Excellent. All right. So good afternoon, good morning, or good evening to everybody. Thank you to the organisers for inviting me. My name is Catherine Trupp, and I work with the Murchison Widefield Array at the International Centre for Radio Astronomy Research at Curtin University, which is in Perth, in Australia. So when Yushan first invited me to give this talk, I was a little bit perplexed because machine learning is not something that we use extensively in the observational space, at least within the MWA. But we do, more broadly, we're talking about being able to extract information from our data sets. Shane, can you mute, please? I can hear you typing.
Sorry.
That's okay. Thank you. About extracting information from our data sets in order to try and extract the signal. And so that's what I'm going to try and address today. So just briefly looking at the talks that are part of this SIP, there's quite a focus on theory. There are observational talks, of course, but there's quite a focus on theory and on machine learning and other techniques like that. And so I thought I would give a little bit of a background on the signal and the interferometry that we're using to actually detect this, because that determines the information that we have available to us. I'll talk a little bit about the MWA as a project and what we're trying to achieve and some of our latest limits. And then I thought I'd try and touch on a few different aspects of some of the work that we've been doing, which is, I'll say it's sort of going beyond the power spectrum. So it's trying to use information more extensively to try and extract information from the early universe, but not just from the variance estimator. So I talk a little bit about some work that have been done in our calibration of our data space with some machine learning. That's some very initial work. And then a couple of pieces of work that have been done to look at extracting the signal in slightly different ways. And I'd just like to sort of touch on the broader questions that I'm not really going to answer in this talk, but it's just worth keeping in mind when we're thinking about information, we're thinking about our data, is what determines success in an EoR experiment, and more concretely than that, how do we confirm a detection? So each of the experiments around the world are getting closer. EDGES reported a detection of the global signal, and SARA-3 has had some commentary on that recently. But as we get closer and closer to actually making a detection, how do we go about ensuring that we can convince the community that this is something real and not just something that's a foreground within our instrument? And so as we get closer, it's worth keeping these sort of questions in mind as we think about how we undergo our experiments. Okay, so just setting the scene observationally with some of the experiments that are being undertaken at the moment and have been in the past. So here we're looking at our redshift space and our very classic picture of a typical evolution of the brightness temperature as a function of redshift and as a function of time. So the boxes here that I have are different types of experiments. So the blue box on the right is the Epoch of Reionisation. This is primarily where the MWA, LOFAR in the Netherlands, and also HERA within South Africa are primarily focusing their observations, although there has been a lot more work and a lot more interest in the epoch of X-ray heating after the EDGES experiment reported that detection of the big absorption trough. And so there has been some work from the interferometers looking for the spatial distribution of that 21 centimetre brightness temperature within those redshifts that are much lower frequency. They tend to be more difficult for us to observe in. The sky is much brighter and hotter. The ionosphere is more active, and we're getting close to the FM radio band. But nonetheless, there's obviously a lot of interesting signal there. And so a few of the experiments have now really worked to start looking at the data in that space as well. This little gap in the middle here is not for any specific region, but it's a part of the parameter space where we don't expect the signal to be overly bright, but our systematics and our foregrounds tend to be bright. And so principally the experiments have been looking at later times in the Epoch of Reionization, or at earlier times trying to look for this absorption trough and the X-ray heating. So we've all sort of seen this picture and some of these nice simulations that are being done that we're looking for this spatial the fluctuations in the brightness temperature distribution, and with an interferometer we're interested in those spatial fluctuations rather than the overall evolution of the signal in a global sense. And of course that encodes a lot of astrophysical information that we're really interested in. Of course it's all these components on the right hand side here that we're actually interested in extracting from that early universe signal, but we need to get there first because the signal itself is very, very weak. So globally, just to be able to set the scene for where some of these experiments are, the ones that I've highlighted in purple here are the ones that are working within the Epoch of Reionization principally and are working in interferometric mode. So LOFAR in the Netherlands, the MWA here in Australia, and also the HERA experiment in Southern Africa, which is really tuned to doing this experiment and is undertaking the experiment in a very different way to LOFAR in the MWA. in the future, when we do have a detection, these very different approaches to observing the sky and analysing our data will be really, really crucial for us to ensure that we really do have a detection and have that convincing argument for the community. Excuse me. So the NWA is a low frequency radio telescope that's located where you can see that red star in the Western Australian desert. It's there because it's a radio quiet zone. It's a long way away from people. It's away from radio stations. So it tends to be very radio quiet. Having said that, we do get a lot of RFI that comes over the horizon or is reflected off satellites and aeroplanes from Perth and also from Geraldton, which is a town 400 kilometres from the observatory. It's comprised of 256 of these tiles. Each of these tiles is 16 dual polarisation dipoles, and they're being formed together for each of them to have one view of the sky. So the 256 of them, we can currently correlate only 128 at a time, and that means that we have about 8,000 measurements of the sky at each frequency at each time step. And it has the ability to observe from redshift 17 to 4, but principally we look in the redshift 6 to 9.5 range because that sits within the Epoch of Reionisation. And it's a relatively compact interferometer, and so we can look at angular scales from 1 arc minute up to about 5 degrees. So it's very well tuned for this experiment. So it's a general purpose instrument. It's observed the southern sky. It looks at ionospheric flux tubes. It's interested in radio clusters, large scale radio galaxies, pulsars, our own galaxy. There's a whole range of different science that's done with this telescope, but one of its primary science goals is to study the Epoch of Reionisation. And here's just a few statistics for you. So the experiment's been running since 2013. We have about 3,500 hours on the sky, and about 2,000 hours have been processed through to their endpoint, although all the data have been touched and have been looked at. So we observe at 3 fields in the sky. They're very creatively called EoR 0, 1 and 2. And those fields are chosen because they are in cold regions of the sky. So they're away from our galaxy. They tend to have a low amount of diffuse galactic synchrotron, although that's something that you just can't get away from anywhere you look in the sky. And they tend to not be near the very big extended radio galaxies. But the field of view of the NWA is so large that it's actually very difficult to get away from the galaxy and from the A-team or the large extended radio sources. And they tend to be in all of our observing fields. And I would argue that those extended sources are one of the primary systematics that's inhibiting our ability to see the underlying 21 centimetre signal. They're on similar scales on the sky to the EoR. They're very, very bright, and they interact with the instrument in a complex way. It makes them very, very difficult to completely remove. And I'll show examples of that slightly later. Okay, so I'm going to change tacks a little bit more at the moment, and I apologise to those people who are interferometry experts. These are very cartoonish, but if you're not an interferometry expert, I just wanted to remind you about how an interferometer works and what it can and can't measure. So on the left-hand side, we have our single dish radio telescope. This is something like Greenbank, the Parkes Radio Telescope here in Australia, the FAST Radio Telescope, a number of them around the world, Jodrell Bank, for example, there's a lot of them, of course. And they if they're a single pixel radio telescope, like in the past most of them were, then all of the information that hits the telescope is reflected up to a single point. And as a function of time, you measure one voltage or one piece of information about the sky. So that means if you want to map out the sky, you need to scan across the sky backwards and forwards and slowly build up all of that information. Alternatively, what we can do is we can build an interferometer, and that's made of N dishes or N antennas, and we cross-correlate the voltage signals between them, and that allows us to actually measure the whole sky, or at least the field of view of the instrument, all at one time. So this provides us with a great deal more information. So a telescope array is like a very, very large dish, but it has lots and lots of holes in it. And those holes mean that we lose information. and that means that our images of the sky are messier. If we have a more complete array with more antennas all filling in the gaps, we get more complete information and we get a cleaner data set out at the end. But nonetheless, this is a limitation of interferometry because there are some things that we just can't measure because of where the antennas lay on the ground. So speaking in terms of a power spectrum where we're working in Fourier space and we're working with spatial scales on the sky, the more complete our array, the more Fourier modes or angular scales we can measure at a time. So what does this look like for those of you who don't usually work with interferometers? So this is just from a really nice simulator. The top left is a simulation of the Australia Telescope Compact Array, which is a 6-dish interferometer here in Australia. With only 6 dishes, you get 15 measurements, and you can see this nice top left model image of what our galaxy might look like. Obviously, that's an optical image. And on the bottom right here is what it actually looks like. You can see there's a fringe across it, and you can also see it's poorly resolved. As we now add more antennas, so 32 antennas with an early version of the MWA, the phase 1 of the MWA with 128 antennas, and then one of the newer versions, phase 2 of the MWA in an extended array, you can see that the reconstruction of our galaxy gets better and better and better. Nonetheless, there are some things that we are not measuring. We're not measuring very fine scales. And in fact, if we zoomed out on this, we'd actually see some copies of this galaxy in different places in the image. And again, that's because we're not measuring that Fourier information in a complete way. And therefore, when we try and make an image, we can see that incompleteness in some artifacts. So mathematically, what's going on here? Well, mathematically, here's our 2 very poorly drawn MWA tiles. They're separated by some distance on the ground x. And the incoming radiation from our galaxy, which is in the far field, hits this antenna first and this antenna second, and there's a path length difference between them that will induce a phase that's relative to the wavelength of that we're observing at, but also the angle in the sky of that galaxy. And so because of that, that is why our interferometer natively measures Fourier modes on the sky, because this path length gives us a phase rotation, which is like a Fourier kernel. And so if we take all of those cross-correlation measurements and we do a Fourier transform, that's how we recover our image. And Fourier transforms are fun for all radio astronomers. Okay. Now, of course, one of the primary ways that we try and extract the 21 centimetre signal is through the second moment of the distribution, or the power spectral density. And we do this because that particular statistic contains most of the cosmological information that we're interested in. Most of the 21 centimetre fluctuations are Gaussian fluctuations spatially on the sky. And the power spectrum is firstly very simple to calculate, but secondly, it adds all of that information together. And so it allows us to take a very weak signal and combine information together in an optimal way in order to be able to pull it out from the noise, which is the primary reason we want to use it. Now, an interferometer, as I've just mentioned, natively measures Fourier modes. Therefore, we already have the Fourier transform of the sky. Our U and V, or our K modes on the sky in an angular sense, are already encoded in our data. And so an interferometer natively helps us to compute the power spectrum. The third dimension, of course, is that line of sight dimension, and we can extract that by observing at different frequency channels. And then that's a Fourier transform that we need to do ourselves. But this is the primary tool that most of the experiments use in order to be able to extract the signal. So this is just diagrammatically what I just said about how we actually go about taking a volume of the universe. We do a 3D Fourier transform, and then we can average our angular modes together. We could also average the line of sight mode together, because we assume that the 21 centimetre signal is going to be isotropic. Then the information in any particular direction should be statistically the same as in the other direction. And so we can add all of that information together. Instead, we often work in this two-dimensional space where we keep our angular modes and our line of sight mode, which is called K-parallel, separate. And we do that because our sky doesn't just contain 21 centimetre signal, but it contains all of these foregrounds. And we need to be able to separate those foregrounds out. So what are those foregrounds? Well, they're point sources. So these are radio galaxies that are unresolved by our instrument. And then there's our own galaxy. So we're talking about synchrotron emission, free emission, other types of emission from our own galaxy that produce very large scale structures on the sky. These are orders of magnitude brighter than the signal we're interested in. And so this is what this is how we want to actually separate those two signals. So working in 2D space, we expect that those foregrounds, because they're spectrally smooth, they're continuum sources. Spectrally smooth means that when we do a Fourier transform, all the information gets contained at the low K modes. And so we expect that the foregrounds are going to be contained in this wedge-like region at the bottom of our two-dimensional power spectrum space. The reason it's a wedge and not just a brick at the bottom is because, as I mentioned before, interferometers don't contain all modes. And because the modes that it does contain change as a function of frequency, you tend to get this spillover of signal further and further up into the power spectrum as you look at smaller modes on the sky. But nonetheless, we try to work here in this EoR window. So the MWA, just to complete the picture on what that looks like for the power spectrum, these are some of the results over the last 3 years that have been published by the array. These are looking at different observing fields. They're also looking at different redshifts and using different methodology, different pipelines to actually analyse the data. And so some of these are very competitive limits in the current research field, but none of them are close yet to actually a detection. We expect to have to get deeper in order to be able to get that detection. And like I said, one of the principal systematics that still exist for us are those large radio galaxies that sit in the side lobes of our instrument that we need to remove more cleanly in order to be able to reach the signal. Okay, so now I'm going to, now I've given that introduction, I'm just going to talk briefly about 3 different very separate projects that look to use the information that we get from our data to be able to prosecute this experiment. So the first one is in the calibration of our data. We know that calibration is extremely important. And if we get the calibration wrong, then we can't do the experiment. So it's really, really important that we understand how well we've calibrated our data and whether data are high quality or not to do science with. So this is work from a master's student from the University of Melbourne, Dom Mendonca, who worked with Bart Pindor and Rachel Webster. And what Dom was interested in looking at was trying to apply a range of machine learning techniques to characterize and cluster the calibration solutions for our data to try to detect anomalous antennas and also anomalous spectral channels. Excuse me. So this was just a really initial exploration looking at the amplitude of the calibration solutions. You can see an example here of where it was able to detect an anomalous channel in what otherwise looked like very clean data. So at the bottom, what you're looking at is, for this particular observation, the calibration solutions for a particular tile at a particular frequency, and they all look quite good. They look quite normal. There's nothing anomalous there. But with this technique, the algorithm was able to extract this anomalous time step that otherwise would have been included in our data. So like I mentioned, this was an initial exploration of how we might use machine learning to look at the quality of our calibration. And after this initial exploration, there's now additional work that's being done, taking this type of approach, but to a much greater extent to look at our calibration solutions for our best data sets. Okay, so now I'm going to talk about moving beyond the power spectrum. How can we use the information in our data a bit more completely than we do just by looking at the variance statistic? So this is just to recap what I mentioned before. The power spectral density, or the power spectrum, allows us to quantify the power in our signal on a given spatial scale on the sky. And so it requires that we take the Fourier transform of our spatial data, and we work in Fourier space. And the power spectrum is it's a Fourier transform, of the two-point correlation function, and it's computed very simply as this ensemble average with a normalization, a volume normalization of the Fourier modes of our visibilities. So it's very simple to compute. And why do we use this? So this is a diagram from Wythe and Morales, I think it's 2010 actually. The signal we're looking for is highly Gaussian, a lot of redshift. So this is the theoretically motivated PDFs of the temperature distribution as a function of scale for different redshifts. And you can see that the signal is Gaussian, quite Gaussian at early times, and develops some higher order terms at later times. But a lot of the information is encoded in that second moment. And therefore, it's a good way for us to extract most of the cosmological information. And it's also very easy to calculate, like I mentioned before. So in a very simplistic way, this is an example distribution of where the tiles are on the ground for the MWA. Here's the core of the MWA. You can see this spans 400 meters across. These are two hexagons, each of which contains 36 of these tiles, and they're designed to be able to match EoR modes on the sky. If we then look at what all of those baselines look like as we take those cross correlations in Fourier space, this is our baseline distribution. You can see in the center here, we have a very high density of baselines. In other words, we're measuring the Fourier modes very, very effectively. And then we'd like to take some sort of average in an optimal way, a weighted average of those data. And we compute the power spectrum just like we would compute a variance estimator. And by that, this is just like a simple way that you would take any sort of data and compute its variance. You take the measurements, you subtract the mean, you square it, and you average it. And in a very simple way, with some weight and optimal weighting, this is what we do with our power spectrum. But of course, that doesn't contain all the information in our data. So instead of just combining the data together in that way, why don't we actually look at how the data are distributed and see if we can extract more information that way? So this is another cartoon on the left-hand side here of, now I've gone into actual K space in terms of inverse megaparsecs, but again, this is just our UV space on the ground. And these annuli all contain information that that for the 21 centimetre point of view is statistically equivalent. So these are different realizations of the 21 centimetre signal in each of these different modes. Each of them is an individual realization. And if we take the variance of that, then that gives us an estimate of the 21 centimetre power. But of course, all of those individual measurements contain information themselves. And so instead of just taking the variance estimate, why don't we actually look at the distribution of the data itself? And I realized I'm running out of time, so I'll just go quickly. But what we did here is we used a kernel density estimator to try to look at the underlying distribution functions of our data. And so we used a Gaussian kernel to look at those PDFs, but really what we're doing is we're histogramming data that we are saying is statistically equivalent. So as an example of what this might look like for a contaminating source like Fornax A, this is a source that's a few degrees across on the sky. It has structures on a lot of different scales. And if we look at the kernel density estimate histogram of that, then what we can see is that on very large scales, this is angle in degrees, on very large scales, there's not very much information, and that's because the source itself is not contained on those scales. But as we move to scales on the sky that have signal and have power for Fornax A, which is sort of, tens of arc minutes through to a couple of degrees, we can see that the distributions here are very, very broad. You can see this is Jansky's. So this is the histogram cut through here. So this is not Gaussian, but it also is a large contaminating source, and understanding what that looks like in our data and how that's contaminating our variance estimate can help us to extract additional information. And so we can look at histograms at different scales and in different wave modes. We can see here in the blue, this is a mode that's very thermally noise dominated. It's very highly Gaussian. Whereas the red line here is a mode that's highly contaminated by foregrounds. And so you can see it has this binodal distribution. It has a lot of cells that have a lot of power in them. And that's that foreground sky, again, causing those problems. So now we can look at different fields. And we can look at what the histograms of our data look like for different fields. We expect the 21 centimetre signal to be statistically the same, but we expect the foregrounds to be statistically different. So how can we use that information in a way to be able to separate out the foregrounds and the signal? And so we can take those distributions and we can look at the moments. We can look at the mean, which is close to zero. It should be close to zero, which it is. We look at the variance, which is like a clean version of our power spectrum. And we can also look at higher order moments. And when we do that, we see that there are modes that are quite contaminated and have all these higher order moments. And those are the ones that contain those foregrounds. So again, this is additional information we can use. All right, so I'm just going to skip forward to the final piece. And this is just a couple of slides before I conclude. And this is the use of wavelets. So when we look at a volume of the universe, it's never strictly ergodic. And that means that from the front of our box to the back of our box, unless it's something that's decoupled from the Hubble flow, there's always going to be signal evolution. So if we're taking a Fourier transform along that line of sight, we're not really doing the right thing if our signal has actually evolved from the back of the box to the front of the box. So instead, what we'd like to do is we'd like to have a sliding power spectrum. We'd like to have something that takes into account the fact that the signal is evolving as a function of time. It means we don't have to carve up our data so much. And of course, a wavelet is perfect for this. And this is an example basis function here. This is the Morley basis function. And effectively what it is it's a Fourier kernel contained within a Gaussian envelope. And that Gaussian envelope can get larger or smaller to allow for the Fourier transform within it to be Nyquist sampled, but to also allow for some signal evolution. So we did some initial explorations of this just from the simulation point of view to look at what the foregrounds might look like in a wavelet space. This is on the right-hand side as an example of what point source foregrounds might look like. And this is a scale from redshift 6 up to redshift 13. So it's a very large depth of the universe. And then we can look at what the 21 centimetre signal might look like, again, with the simulation in a wavelet space. So we actually tried to do this, and this hasn't been published. And the reason it hasn't been published is because there's systematics in these data that mean that we need to fix before we can do this. But we can take a very wide bandwidth observation from the MWA. This is 450 hours. And we can do a wavelet transform on that and see if we can extract additional information than we could otherwise do if we carved up our frequency data sets. We need to then interpret these data, and that's some work that's been done by Brad Gregg, Stephen Murray and Tom Binney. But certainly I think that the wavelet space is a good way to approach some of the larger data sets that we have. All right, so I'm just going to finish there to say extracting information from our data is really crucial for EoR studies. And calibration and telescope diagnostics provide data quality information that lend themselves to machine learning techniques, and that working beyond the variance estimator can provide additional information both about the 21 centimetre signal but also about the contaminating foregrounds. And I will stop there. Thank you.
Yeah, thanks, Kirsten. There are actually already some questions in the Slack channel. I put several of mine. I will start with other people's question, but I actually saw Baron here. Baron, do you want to just ask a question by yourself?
Yeah, am I audible?
Okay. Yeah.
Yes, so I was thinking, how far can we go towards the large scale in order to detect the signal without affecting by the foreground? So, is there any estimate?
How far? Sorry, I don't understand the question.
How far can we go towards the large scale in order to detect the signal without getting affected by the foreground?
Oh, look, we're affected by the foregrounds on all scales because the foregrounds exist on all scales. So we really need to deal with them. We can't just get away from them.
Okay.
Josh.
Nice talk, Kath. I'm curious if you could help me get more intuition for the shape of the foregrounds and the EoR in that wavelet basis. it had that kind of like U shape almost.
Yeah, I think so. I did that work a while ago, but part of it is the fact that the cosmological transformation is evolving with redshift, and so that changes the mapping from eta to K parallel. And there was also that it's also that the point source signal and the telescope system equivalent flux density will change. I have a more complete answer. I'll put it in the Slack for you. I'll just have to page it back in my brain.
Thank you.
Quintin?
All right. So, how have you been treating ionospheric distortion for MWA?
Yeah, that's a good question. At the moment, what we do is we put all of our data through an ionospheric quality assurance metric, and we only use quiet data. We are working on techniques to be able to correct the data for ionospheric activity, but at the moment we don't have that in place, and so we're really working the quietest data set where the ionosphere is not a problem for us.
All right, thank you.
I actually want to follow up on what Josh was asking. So I would like to understand more about this wavelet method. I heard Brad talking about this several times, but is it simply just to use the several peak within the wavelet? So because you observe the signal between A to B megahertz, and then you just use the peak in the wavelet to somehow pick up the signal between signal in different frequency within this frequency range. Is that the whole idea?
I mean, effectively what it's doing is that the wavelet is placing an envelope over your redshift space, and then the Fourier transform is happening within that. So it's centered at a particular redshift, but you still effectively have a box. It's just the box that's shaped by the wavelet envelope.
Then how do you see the evolution, the redshift evolution?
Yeah, that's right. And so then that then moves along redshift space, and you do that little transform as you move along redshift space.
So you actually move the wavelet. Okay.
Yeah, that's right. The wavelet moves.
Yeah. Okay, I still have like 2 small questions in the Slack channel. So if you have time, maybe you can go there and help me understand them. I think we can move on to the next speaker. And I believe we are missing. No.
I think that he arrived.
Yeah.
Shingo, are you here?
Hello. Yes, can you hear me?
Yes, we could.
Perfect.
Can you share your screen? Yeah. Okay. Next, we have Shingo Tanigawa
Yes.
from Subaru University, I believe. Okay, go ahead.
Okay. Hello, everyone. My name is Shingo Tanigawa, and I've been working on developing a machine learning model, machine learning photoset model that is trained on simulated data. And today we'll talk about our recent results and some future plans. So first, I will talk about the overview of this project. Galaxy redshifts are the key component in the application of large imaging survey data and representing the measurement of galaxy distances. And in the context of upcoming large imaging surveys, extragalactic astronomy will significantly benefit from photos estimation at an unprecedented level. So efficient and accurate photos estimation is a topic that is fundamental importance in various fields of study. So the aim with this project is to develop a novel photosy model using machine learning techniques, which can be used for exploring an unprecedentedly large volume of photometric data, and also apply to a broad redshift range, particularly up to very high redshifts in the early universe. And traditionally, photosets have been estimated by a template fitting method, which can be generally applied to any redshifts. But its performance is fundamentally restricted by the template set. On the other hand, the benefit of ML is to learn from data and potentially outperform template fitting. But one critical drawback is it cannot work outside the SPECset training range. And there are also some other benefits in using ML techniques, such as time efficiency, robustness, and flexibility, and etc. And some previous studies have actually demonstrated the capability of ML photos codes, and different ML algorithms have been utilized in previous works on photoset study. And one significant model closely related to this work is DeepSet. And they have demonstrated their ML model can outperform their template method for photo-Z estimation. But it did not go outside the low Z training redshift range. So based on these results, we are targeting objects at much higher redshifts than most previous works. So what is novel in this work is we train a model on simulated SEDs in a broad redshift range, which are generated from the best fit SEDs for real low Z galaxies derived with the template fitting code EASY. We use EASY since it is one of the state-of-the-art photo-Z codes, and which are also commonly used for a broad redshift range. And what is important is we do not need high Z spectroscopic data for training a model, and no physical models are also required for producing mock SEDs. And in this work, we use the catalog data generated by Stratman, which contain 5 medium band photometry obtained from the Z-Foch survey, and imaging in 3240 filters from publicly available surveys as well. Now we'll explain our experimental methods. So regarding the overall structure of the model, it is simply trained to minimize the loss, whose performance is then evaluated based on the photo-Z error calculated as the difference between the recovered and true redshifts divided by 1 plus Z true, which is defined as delta Z here. And we employ 2 indicators commonly used in most photo-Z studies. One is normalized absolute median deviation of delta Z, called NMAD, which is robust to outliers and thus represents photo-Z errors of, so to speak, ordinary samples. And we also define the outlier rate as the ratio of the number of the test data whose absolute delta Zs are over 0.2. So we first generate artificial photometric data of simulated galaxies, which are used for training the photo-Z model. And the model is optimized for photo-Z estimation using k-fold cross-validation to explore the most appropriate ML architecture and tune its hyperparameters. We then train the selected model on the simulated data, whose performance is evaluated on the real catalog data. So it is thus eventually tested on the catalog samples with spec sets. And the result is compared to the performance of EASY in terms of NMAD and outlier rate. So let's have a quick look at our simulation method to produce mock SED data. So we obtain observed galaxy fluxes from imaging surveys, which are fitted with EASY. And the low Z best fit SEDs are artificially redshifted to arbitrary redshifts, whose photometry is simulated using the transmission curves of the filters. And lastly, we apply the errors of the catalog sources to the simulated fluxes to produce realistic photometric data. So there are 2 major steps to generate simulated datasets, SED redshifting and noise application. So regarding the artificial redshifting of SEDs, you can see the overall process from this very brief movie. And the simulated SEDs are generated from the entire low-Z samples. So our simulated data preserve the population of galaxies at low-Z. And following the generation of artificial SEDs, we simulate photometry with noise, and we assign a set of errors extracted from the test samples to each simulated galaxy by selecting observed data of similar SED shape. And one benefit of this method is we can empirically apply realistic noise to simulated fluxes. And another is we can also incorporate information on missing data into the training sets in a direct manner. We thus do not need to impute missing values included in the test catalog samples. And based on the results of hyperparameter optimization, we selected the FCNN consisting of 5 layers with 200 nodes. Following each intermediate layer, our RE-LU nonlinearity is 5% dropout and batch normalization layers. And the output vector contains probabilities for 100 redshift class bins up to a redshift of 5. And we take the recovered redshift from the bin that has the highest probability. So the redshift estimation problem is handled as a classification task with the redshift classes ranging between 0.0 and 5. And we then address the question of if ML models could be comparable to or outperform template fitting methods. And we also investigate if transfer learning can improve models' performance, which has been demonstrated in some previous studies. So we first train a model on simulated data and only retrain the last layers of the networks or real data with spec sets. And this method is more robust to overfitting than training a model from scratch on datasets of limited sample size. And I will now show you the results of these experiments. So you evaluate the photo-Z statistics for ML and EZ with a bootstrap method used to estimate stochastic errors on the indicators. And the table shows the results for CDFS and Cosmos field data. And for each field, we can see the number of band filters, the number of spec set data, and the scores of NMAD and outlier rate for ML with transfer learning, and EZ. And overall, the NMAD and outlier rate show no significant gap between ML and EZ, regardless of the field. And regarding the application of transfer learning, the outlier rate shows no significant improvements, but a photo-Z precision represented by NMAD is slightly improved by transfer learning. And what is particularly important here is the model can also perform well exclusively on the subsamples of high-Z galaxies, although our simulated data are originally generated from the observed photometric data of low-Z galaxies. So this indicates our method can be applied to a high redshift region beyond the low redshift range of the original observed data. And we can further explore the relationship between photo-Z errors of EZ and ML from this figure. And it shows delta Z EZ versus delta Z ML plots for the spec set test data of Cosmos. And their whole distribution is presented in the left panel. while the zoom in plot within the outlier threshold of 0.2 is in the right panel, respectively. And what is most conspicuous is on the right-hand panel, the data points are gently aligned along with the diagonal from the lower left to the upper right. So this means the photon errors of EZ and ML for the individual objects are quite similar, and thus indicates they are systematically correlated with each other. So we conclude the ML photon network almost achieves the photon precision comparable to the state-of-the-art template fitting code EZ, but it requires much less computational time than EZ, running about 100 times faster in photon estimation. And another thing is the ML model can adapt using the spec set information with transfer learning. And one remaining issue is the possibility of further improving the quality of simulated data. This can be understood by the results of the transfer learning, which significantly improves the photon accuracy. So one explanation of this is there still remains a gap in data quality between the simulated and observed datasets, which can be corrected with transfer learning. And there are many significant JWST surveys that will offer a massive amount of high quality photometric data with broad wavelength coverage at IR. And unfortunately, I think I won't utilize data from most of these projects during my PhD, but the data released from the ERS programs could be in time for this project. So we plan to further improve the baseline model considering the progress of these survey projects. Thank you.
Okay, thank you.
Very nice. Thanks.
Nice presentation. And we have time maybe for one or two quick questions if someone have some. Otherwise, we'll read the one from the Slack. Or Misha, I don't want if you want to go ahead with your question.
Yeah, I want to ask if have you compared the the ECU, the result from ECU give the probability of redshift at each redshift, and have you compared the probability the P of C results between the learning and the easy one?
You mean the quality of PDF of redshift?
Yes, PDF.
Okay, yeah, yeah, that's a good question. Okay, I have it. So yeah, one reason why we made our model as classification model is we can obtain the PDF for redshift rather than a simple point estimate, and which could be useful for analyzing the derived redshift in a probabilistic framework. And this is one of the example of our derived PDF. And we have also tried PID test, and the red line is for ML and the blue line is for EZ. And I think there are many things to be considered, but if the predicted PDFs are well calibrated and reliable with respect to spec sets, the histograms of the PID values is uniform. And as a quick look, we evaluate the reliability of the output PDFs with the PID test, and the PID distribution of ML exhibits a slight over dispersion, but generally stick to the uniform line. why the PDFs given by EZ are somehow polarized to an under dispersion at the extreme PID values. So yeah.
Thank you.
Sorry, yeah.
Okay. There are other questions in the Slack channel. If you are happy to answer them, but now we have to move to the next speaker.
Thank you.
Can you stop the share screen? Okay, thank you. So our next speaker is Kana Moriwaki, a PhD student from the University of Tokyo. And so whenever you're ready, you can start.
Okay, thank you. I'm Kana Moriwaki. I thank the organizers for giving me a chance to talk our recent work in this great workshop. So yeah, I will talk about our recent work based on these papers. So first, I would like to briefly show what we are going in this talk. So basically, we will do a signal reconstruction from the observed data. So the observed data is some kind of combination of two different emission line signals, and we use the CNN to separate these signals. So I show the video of the process of the training of the CNN. So as you can see, at first the CNN reconstruct very random signals, but at the end of the training, like this, the signals properly reconstruct the two different signals from this confused observation data. So let me explain what we are doing in this study. So basically, we focus the large-scale structure of the galaxies. And yeah, here I show one example of the distribution of galaxy from SDSS. And as you know, if we want to know the distribution of galaxy, especially the three-dimensional distribution of the galaxy, we need to do a very deep observation, detailed spectroscopic observation to detect the individual emission line from the galaxies to measure the exact redshift of the galaxy or the distance of the galaxy from us. But actually, this detailed observation, spectroscopic observation, is very costly and takes a lot of time. So it is a bit difficult to observe a large volume. So then the question is how we can observe the large-scale structure more efficiently. Then one possible answer is to adopt the coarser resolution and do the same spectroscopic observation like this, and to detect the integrated light emission from many galaxy samples at similar redshift to detect the large-scale structure. So this method is just called line intensity mapping. And you may all know the line intensity mapping of 21 centimeter, which can be used to detect the cosmic reionization signals from the very high redshift. But basically, we can do the same thing for the emission line from galaxies like C2CO, or the other optical and UV emission line like H alpha, O3, and Lyman alpha. So, and here I show a list of future line intensity mapping observations. So there are basically a lot of planned observation. And basically, we can do large-scale structure observation over a wider or higher redshift. So we can study a lot of things with this, including galaxy formation, evolution, cosmology, and cosmic radiation. So this is very promising method to detect the galaxy large-scale structure. However, there is a very serious problem in the line index mapping observation, which is called line confusion problem. So let's think about what if we observe this kind of spectrum at the single pixel of the entire sky. So this signal could, you may think that this signal is due to line emission from the galaxy. However, we cannot tell which kind of emission line. So emission line from high redshift galaxies or low redshift galaxies. So we can basically not distinguish these contributions. So we don't know which line or which redshift. And actually, this is so-called line confusion problem. And actually there are a lot of methods to deconfuse this line contribution, including cross correlation or anisotropic power spectrum method or masking, etc. But let me show how the line confusion problem affect the observed signals in more detail. So if there are a lot of galaxies along with the line of sight like this, then if the individual galaxy has only a single line emission like this, then the observed spectrum will be something like this. So this just trace the three-dimensional distribution by galaxies. But if the individual galaxies have more than two emission lines, in this case line 1 and line 2, and then the observed spectrum will be something like this. So we observe this red spectrum, and if we bring observed map at a single observed wavelength, then the observed data will be a combination of the foreground large-scale structure and the background large-scale structure traced by two different emission lines. So this is line confusion problem. And we propose to use deep learning, or more specifically a convolution neural network, to separate these different emission contributions. And in this study, we demonstrate how how the CNNs can be used to separate these signals, assuming futuristic spherics observation, which observe this kind of wavelength range, and we can study in this observation we can study emission line like H alpha or 3 from this redshift. So for training the CNN, we first generate a lot of mock observational data using simulation. So simulation and semi-analytical code. Then we develop a CNN that take an input of observed data and output individual emission line like H alpha or O3. So in the CNN, there are 8 convolution layers like this, and that is followed by 8 deconvolution layers. Then in the training, we evaluate the CNN performance by comparing the output result with the true intensity map that is generated by our simulation method. And yeah, in the training, we actually used a training method called generative adversarial network, or GAN. So in this method, there are 2 CNNs called generator and discriminator. So generator is the one I showed in the previous slide. It generate a H alpha or O3 map from the observed or combined map. And on the other hand, the discriminator try to distinguish true intensity map data or fake map. Fake map is the reconstruct data by the generator. So this tells difference between these two, fake and true data. In the training, the generator and the discriminator are trained in an adversarial way, and more specifically, the generator tries to decrease the loss function defined by this, and discriminator tries to increase the loss function. So they are trained in adversarial way, and at the end of the training, generator is expected to be a very good separator of these signals. So this is our method. This is basically our method. So here I show the result of our CNN separation. Here again, I show the observed intensity map at this wavelength, which is a combination of H alpha and O3 at this redshift. And the bottom panel shows the reconstructed H alpha and O3 maps. And this is the combination of these two maps. So as you can see, the CNNs indeed would generate the right distribution of H alpha and O3. So surprisingly, these weaker O3 emission like this are also well properly reproduced by our CNN. And we found that the detectability of the bright signals as large as 70% for H alpha, and also it was about 30% for O3. Actually, at this observed wavelengths, the O3 emission is a bit weaker than the H alpha because it is at much higher redshift. But even though the O3 emission signals are very proper, a part of the O3 emissions are very properly reproduced. And we have also found that the statistics such as power spectrum are also well reproduced for both H alpha and O3. So we had done a demonstration that the CNNs can indeed reproduce or separate two individual signals from the observed data. So this is our first result. And nextly, I'd like to talk about the three-dimensional data. So actually, so far, we have only used the two-dimensional data that is observed at a single wavelength, observed wavelength. But in actual line intensity mapping observation, we obtain three-dimensional data like this, three-dimensional large-scale structure data like this. So this observed data is a combination of, again, H alpha and O3 at different redshift range like this. So such a information in the spectral direction could also be a very informative to the CNN. So we will use such a data for our separation problem. So the point of using the spectral direction information is that we observe the same large-scale structure data at the same redshift at two different wavelengths. So for example, the redshift 1.5 large-scale structure is observed at this and this wavelengths, and they are traced by different emission line L3 and H alpha respectively, and they are separated by this range. So we can basically use this information to improve our CNN. So to tell the CNN that the two different wavelength range have a kind of a same large scale structure data, we modify our three-dimensional CNNs a bit like this. So this figure shows the architecture of a improved CNN, in which it takes two input, this orange box and yellow box, which have a same redshift range traced by two different emission, H alpha and O3. So the CNN combine the information in these two to intensity map, in which the same logical structure are buried, and then do some kind of analysis to output H alpha and O3 signals. So yeah, then so it is supposed that by doing such a, by adopting such a kind of physics-informed network architecture, the networks, so it is more easier. It is easier for the network to separate the two emission signals. So here I show the reconstruction result. Here again, I show the observed three-dimensional intensity map. By the way, I forgot to tell you, but in this study, we also include the telescope noise, just a Gaussian noise, in addition to the H alpha and O3 emission. So this is observed map. And from these, the CNN, 3D CNN, reconstruct the O3 emission signals like this. So you can compare this with the true distribution of the O3. So as you can see, obviously the bright sources like this are very well reconstructed. And I'd like to say that the reconstruction result for H alpha basically the same. So, and also the reproducibility of the individual bright peaks as large as 80% for H alpha and 70%, about 70% for O3. So compared to the two-dimensional case, the detectability is improved very much. So this is we consider that this is all owing to the physics-informed architecture. So this is basically the result of a recent study, and here I show the summary. So we proposed to use machine learning to solve line confusion problem, and we had a two examination with using a two-dimensional line test mapping data and three-dimensional one, and we have shown that the CNNs trained or conditional GAN can be used to separate two or more line signals from the confused line state mapping data. So basically that's all. Thank you.
Yeah, thanks. Thanks, Kana. I think unfortunately we couldn't do Q&A. Now we are running a bit late, but there are several questions in the Slack channel already. So please go and check. And let's move on to our next speaker, Nisha Liso Chawadit. Yeah, okay, Nisha, go ahead. I'd like to remind the speaker that the talk is 15 minutes. So if you want some question time, maybe try to finish at around 13 minutes. Thank you.
Okay. Hi everyone, thanks for coming in. So I will today I'll talk about the work that we recently published. I will tell you how biases in UV luminosity functions can be induced by different completeness correction methods. So this work investigates an old age quest of how to turn number counts to volume density. Specifically, we are looking at how to turn the number of high redshift Lyman-Break galaxies into the UV luminosity functions. So one of the important steps in determining the luminosity function is to account for the missing galaxies, because these high redshift galaxies are not only very faint, they can be blocked by all sources of foreground objects like galaxies, stars, or even cosmic rays. So the most common way to account for the missing galaxies is to use the completeness simulations. And the most simple explanation is that we create many galaxy stems, put them in the image, and then try to see how much we can recover using the same method that we apply to the real galaxies and what fraction we recover. So this method has been used in, I would say, like all of the UV luminosity functions determination. However, the difference between the works come in at how they store the results of the simulation. And after reading through literature, I can group them into three main categories of methods that I will go into detail later. And interestingly, the works that use different methods, sometimes they yield the luminosity functions that are in mild tensions with each other. For example, there are suggestions that the UV luminosity functions at high redshift may not follow the Schechter functional form. So what I show you here in purple is the Schechter function, and that there are works that suggest that there may be an excess of the galaxies at the bright end. So there are more bright galaxies than what predicted by the Schechter functions. So my work here is to evaluate these three methods, whether they always yield the same result, especially in the presence of flux scatter. So now let me go back to the details of how completeness simulation works. So let's say that in the simulation, we inject a number of galaxies, then we can interpret the result with this table where we record the number of the recovered galaxies at different recovered magnitudes. So for in this example, if we inject 100 galaxies in each magnitude bin, and here what are the number of the recovered galaxies at different recovered magnitude. And what I would like to note that in this example is the ideal case, ideal scenario where the number fall into one-to-one line. So in other words, we can recover the exact flux that is input. So there's no loss in the flux of flux scatter. So now the difference between the methods come into the definition of completeness. So the first method, the completeness is a function of intrinsic magnitude. So it's basically a fractional sum in the vertical direction. And in this example, the completeness at this pink box, pink magnitude, is 50%. And for the second methods, they define the completeness as a function of recovered magnitude. So they sum the fractions in the horizontal direction here. And in this case, the completeness at this magnitude, the recovered magnitude, is also 50%. And the third group, they define it as a function of both recovered and injected magnitude. And for example, in the completeness at this cell value is also 50%. So now you can imagine that if there is flux scatter, then all the numbers will not match. So in this example, these are the completeness at the same value of magnitude for all the three groups. And of course, these completeness definitions, they will be applied to the data differently in order to calculate the final UV luminosity functions. So in the paper, I initially tested three methods with using a theoretical test where I create a mock observation of half a sky size, and we use the same mock simulations. And here what we found. So we found that for the method one, the recovered luminosity functions can be as large at the brightest end in the presence of flux scatter. So what you see here, the black color show the true luminosity function that we try to recover. And we can only recover in the case perfectly in the case of no flux scatter, or the one with really low flux scatter of less than 0.1 Mach is still doing fine. For the second method, we find that the recover UV luminosity function can still bias large when we use when the simulation doesn't inject galaxies with the correct shape. So what I mean is that, so for this method to work, we cannot inject the number of galaxies, the same number of galaxies into each bins. Like in this example, we cannot inject all 100 galaxies into all the bins. So for this method to recover the correct UV luminosity function, it has to inject the number of galaxies that it has to inject must match the shape of the luminosity function that it is trying to recover. So for example, in this case, it has to inject a lot more faint galaxies for it to work. And lastly, as expected, method 3 works well in the presence of flux scatter because it is just the function that uses the most information from the completeness simulation. And what you see here are the results from stochastics, because there are just not many data in this magnitude bins, which cannot really be avoided. So aside from those theoretical tests, I also tested the 3 methods on real data using the good south field and the XDF field. And I also developed a completeness simulation code called Glacier 2, and which is now available publicly on GitHub. So please feel free to check it out if you are interested. So the results we found from the real data is that we generally see the same trend as we see previously. As you can see here, method 3 yield the most consistent luminosity functions regardless of the flux scatter, while the other 2 methods can bias large when flux scatter is high. But in any case, the UVLFs, the luminosity functions that we recover, they do not differ from each other by more than 1 sigma. So this means that the uncertainties in the data we use here are still dominated by small number statistics. However, we hope that this work will raise some of a caution to check whether the excess in the bright end, especially in the bright end, is systematically biased, especially in the coming flux of data from JWST and Nancy Grace Roman Telescope. So I will finish with this conclusion slide and taking questions.
Yeah, thanks, Nisha. Yes, actually a great talk. So any questions for the audience? Maybe I can start with mine. So at the beginning, you showed that at high luminosity ends that the different observational group gives different luminosity function. So I was wondering, are they using the same, like the data from the same field? Or,
no, they use different data sets.
If they are using different data sets, then is it mostly dominated by cosmic variance? It just, you don't,
yes,
in some
possible.
fields.
Yes, it's very possible, but if you actually look at it, the ones that like the pink ones that only give upper limits in this, it's consistent with my result that the ones that use the pink ones is here the method 3, so they give the smallest number of bright galaxy, the smallest volume density of bright galaxies.
Yeah.
while the other two they derive larger.
Yeah.
But it's I mean I yeah, definitely we don't know the data, but I mean yeah, it's shortly data.
Maybe if you can also quickly comment on the bias in the phantom end, because I also see in the recovery results there's also some difference in the phantom end.
Yeah, so from here so the bias will happen whenever there's a steep drop in the number count. So the personally I'm not worried about the phantom end as long as when we do the fitting, the luminosity function fitting, if we discard the bins that are like highly incomplete.
Yeah, okay.
These are just cause it's the drop from the incompleteness.
Okay. Okay. If there's no more questions, let's move on to our next speaker. Nicha, could you please stop sharing? Okay. Our next speaker is Xiaoshen Zhao. Xiaoshen, could you please share your screen? Yeah. All right. Go ahead, please. Hello, we couldn't hear you. Okay.
Hi, everyone. I'm very happy to be here to talk about our recent work, the simulation-based inference of reionization parameters from 3D tomographic 20-centimeter light cone image. My name is Xiaoshen Zhao, a PhD candidate from Tsinghua University, and here are my collaborators. So this is my content. And first, I'll give a very brief introduction about the background of this work. As we know little about early universe like the EoR, while the future HERA and SKA will enable us to take the 3D image of the EoR with the technique of the intensity mapping. And ideally, the 21-centimeter image might look like this. Here we show a Doppler signal created by the 21-centimeter fast, without any instrumental effects, of course. And with this kind of image, we can infer the physics, either the astrophysical parameters or cosmological parameters of a model. And in this work, we focus on the astrophysical parameters. And some works have been done to perform the parameter estimation with image, both the 2D image and 3D image, where the posterior inference is not well considered in the 21-centimeter cosmology literatures using machine learning, except some efforts with Bayesian neural networks, or BNNs for short. People with interest could refer to these papers. And so let me give a brief introduction about methodology. We first train a 3D CNN, which take the 3D light cone image at the input and output the two astrophysical parameters: the minimum virial temperature of halos that host the aerolyzing sources and the aerolyzing efficiency. We know that the trained neural networks could be regarded as the data compressor to produce the data summaries from the light cone image. And then we integrate the 3D CNN into the whole inference framework called the Delphi 3D CNN. Let's start from the parameter theta, and we can produce light cone data D with the simulators like the 21-centimeter fast. And then we apply the trained neural networks, like we mentioned in the last slides, to perform the compression of the light cone data D into some very low dimension data summaries T. And then with the parameters and the corresponding data summaries, we could apply the neural density estimators, or NDEs for short, to fit the model to the conditional density of the data. After that, at any observations, we could evaluate the likelihood. Combining with the parameter prior will enable us to get the parameter posteriors, which will be sampled with the MCMC-like method. So let's have a closer look at one of our NDEs, the MNF, where its full name is masked autoregressive flows. It's a kind of normalizing flows with masked autoencoders for density estimation, or MED for short. Basically, the idea is that the data summaries following the potential target distribution could be transformed into another variable, which could follow a very simple distribution like the normal distribution. And this kind of transformation is composed of a flow of individual transformation, which are realized by MED, it's listed here. In this form, we could write down the conditional density with the normal distribution and the Jacobian of the inverse transformation. We first train the MAFs with the parameters and summary pairs to fit the conditional density, and then we evaluate the likelihood between MAFs at any observations, and finally we could get the posteriors. So let me present some results. First, we focus on two specific realization models, which both match the latest constraints on this electron scattering optical depths. For the band galaxy models, the universe might realize earlier but with smaller bubble size, while for the bright galaxy models, the universe might realize later but with larger bubble size. And we compared our Delphi results in blue with that from 2020 MMC using the parse filter at the statistics in red. The Delphi results have kind of fatter contours. Well, if we focus and marginalize the distribution for each parameters, we can see that the Delphi results have tighter constraints, especially for the bright galaxy models, like this. After we have trained the NDEs, we could evaluate the parameter posterior, giving a new observation very quickly. And here we show the predicted values versus the true values for each parameters from another 1,000 mock observations. And we plot the medians together with 1 sigma errors from each posterior. From the medians, we can also compute the R-squared values, which both have improvement compared with the 2D CNN literatures. And another important topic is the validation of the posteriors, which basically investigate the statistical deviation between the inferred distributions and the true ones, from which we could pick more accurate NDEs. For the time limit, I'm not going to talk about this topic, but in our papers, we present a very simple example to realize the validation of the posteriors. And we know that the data compressor could be replaced by any other compressors. So in a follow-up work, we apply an alternative compressor, the scattering transform, to the original 3D CNN. And actually, the scattering transforms share the similar spirit as the wavelet transform introduced in Cho's talk just now. And for more details about the scattering transform, please see the next talk given by Professor Jensen. So after we replace the 3D CNN by the scattering transform, we got much better constraints on the two parameters, which might imply that it might be hard to efficiently train a traditional or an usual CNN. To help my summaries, we perform the base inference of the realization parameters, where the likelihood is implicitly defined through 4 simulations. The 3D images are compressed into informative summaries with the trained 3D CNN. The results are performed the 2D CNN and the likelihood assumed base inference from power spectrum with 2020 MC. And the 3D CNN could be replaced by other compressors like the scattering transform. That's for any questions.
Thank you, Shashank. And so if anyone has some questions, please raise your hand and just make your question.
I can start with mine. I was looking at your recovery, and that's good there's a comparison with the MCMC results. So it looks like both of the DEFI results are broader compared to the MCMC results, and especially without the scattering transformer, you are missing the models in the bottom left. So you are missing the models with low eta, low temperature. Do you have any comments on that?
You mean these slides, the lower left region?
Yeah, I think you can also use these slides, but it's more obvious in the previous slides. So if you look at the 2D contour, like you don't actually see the models with which can be seen in internal CMC results, but you don't actually see it in DEFI's results. So you don't actually see models on the bottom left corner.
Yeah, you mean the degeneracy shape?
Yeah, so it looks like the degeneracy is less significant. So just wondering if you can comment on that.
Yeah, I think it's mainly caused by the trend 3D CNN. So I mean, it is hard to change a perfect CNN. And from my point of view, if we make further efforts to train the CNN, maybe we could have different results. Maybe it will show more degeneracy shape, like the 21 CMMC results, or it might have a less degeneracy shape. It depends on the data compressor, the CNN we used in this work.
Okay, but the horizontal and vertical line in the 2D corner in the 2D PDF is the true model, right? So it shows that DEFI is actually performing better than the MCMC. This is quite interesting to me.
So my idea is that the uncertainty is more important compared with the median values. So
okay.
Yeah. The inference results could have some variance, but if the true value is within the uncertainty regions, it's also okay. But so our DEFI results, especially for the bright galaxy model, we have a tighter tighter constraints as for the one-dimensional distribution. Yeah, that's the maybe the main improvement.
Okay, thanks.
Yeah, sorry.
All right, I don't see any other more questions. If you have more questions, just leave comments in the Slack channel. So we can move on to our last talk in this session. So our speaker is Yuansen Ting from NU. Go ahead.
Okay, can you see my slide?
Yeah, perfect.
Okay, good afternoon, everybody. First of all, thank you very much, the organizer, for the opportunity to talk today, and thank you very much, Xiaoshen, for the segue at the end. So as Xiaoshen has alluded to, we all know that deep learning is amazing because deep learning can characterize a very complex system. But the question that we try to ask, like in this talk, is whether or not we could have analytic tool that can perform as well as deep learning. And turn out that the answer to that is yes. And I hope to convince you with that. So as we all know, cosmology is very different from astrophysics in the sense that we are not looking at individual object at a time, but rather we are looking at the patterns that are spanned by billions and billions of objects, right? And so the key terms here is the patterns. And the question is how, seemingly this very complex patterns, can we come up with a simple mathematics that can describe these seemingly stochastic and unruly patterns? And one analogy that I love to give is basically like the thermodynamics. It seems like you have a very complex system, but if you can look at the system in the right way, then it will lead to the 3 laws of thermodynamics. So it is possible to come up with very simple like mathematics that describe very complex like patterns. And to understand that point, to further understand that point, I love to explain things in these 2 axes, where the x-axis is what I call the true information of the system, and the y-axis is sort of the uninformative stochasticity that we try to reduce. So let's say if I have an elliptical galaxy, this is of course a very simple object, because we long know that we can summarize this n pixel like dimensional like object with only a summary, a statistic of 3 dimensions. Of course, we like even we are looking at more complex objects, the fundamental process of what we call physical like modeling are still quite straightforward. So the idea here is to project out the uninformative variability. And most of the time, this uninformative variability manifests like itself in the context of symmetry, right? So take the elliptical galaxy, for example, you have the rotational like symmetry that you do not need. So when you try to do the physical like modeling, you try to reduce that out. But this, of course, is a simpler case because we are looking at object-based astronomy. But we are more advanced because we are cosmologists, which are more complex, right? So we're looking at stochastic random field. When you're looking at stochastic like random field, then it becomes less clear what symmetry do you have and how do you reduce that. But even though this seems to be more complex, but the rule of thumb is quite similar. So like if you think about the power spectrum that we all love and like, fundamentally what we are assuming is that the system has translational invariance. And from that, we can try to compress the information. But unfortunately, the power spectrum, of course, is just a subset of a symmetry that we have in the system. It's not all the symmetry in the system. And this is why you can have 2 systems that looks very different, but they have the same like a power spectrum. Or put it simply, right? And this, of course, has a real life like consequences. So if you look at weak lensing, for example, if you use the power spectrum, of course, you get a degenerate like constraint between the sigma 8 and omega m. Or put it simply, if I have a Gaussian like random field, translational invariance is what we have. So taking the power spectrum would have exhausted the symmetry. So you get to a very good mathematical like description of the data. For non-Gaussian or random field, the translational invariance is just one of the symmetry. And this is why when you try to do that with the power spectrum, you lose some of the structural like information. So of course, like this is why we are all here. We all love deep learning. So the hope is that deep learning can capture more symmetry in the system implicitly, that leads to a better like representation of the patterns. But I would also argue that this approach of pure deep learning turned out to be quite dangerous as well, because if you look at the pro and cons of the 2 methods, like this become quite clear. So on the one hand, the power spectrum is what we love because we are really doing physics. We are trying to compress the information. But of course, the bad thing is that it's very lossy, right? CNN, by definition, is more robust. You can think about that is that you try to exhaust the information in the data. But of course, you are not doing physical modeling. So if you trust what I mean, like physics is always compressing the information. Like neural network is anti-physics because you are diverging the information to millions of neurons in the neural network. Or in this diagram, the neural network is actually increasing the stochasticity of the system instead of reducing it. So what do we do? So like part of my group has been quite interested in understanding how do we get the best of the 2 worlds? Is it possible that we can have deep learning performance, but with pure good and old analytic tools? And the answer to that turned out to be yes. And the key to that is understanding why machine learning works in the first place. Most of the time, we treat machine learning like a black box But sometimes you need to open up the black box and try to understand why it works. So of course, we are not the first one to want to do that. Even back in the first paper from Jeff Hinton in 2013 about deep learning methods. Soon after, there are a group of people mathematicians try to understand why CNN works. And turns out that there is actually a very rich field of mathematics that come from it. They call the scattering transform. So I will not get into the details about the scattering transform. I will give you a simple example. What is the key insights here? Why CNN works? So let's say I take a 1D distribution, right? X drawn from P of X. How would you come up with a summary, a statistic that characterizes this distribution? The most naive way will be taking the second moment, which is the power spectrum. And this is actually not bad because you are actually characterizing the variance, which is one characteristic of the distribution, but not all. For example, you misses the skewness. Of course, I'm not the first one to say that you need to go beyond the second moment. This is all cosmology is about for the last 20 years, where people try to say, well, if second moment do not characterizes the map, why not we do endpoint function? So we do higher order moment to characterize the distribution. But I do believe that this is really a rabbit hole that the cosmologists has put themselves in for the last 2 decades. And this can really be easily visualized in the following. So even in the 1D case, right, not a stochastic, a random field, if I have a 1D distribution and I try to take the nth order moment, what I am trying to do, of course, is amplifying the tail. And this is why we can characterize the tail with the nth moment. But the problem here is that as you are amplifying the tail is exactly the region where you have the least sample. So you have actually the most sampling noise. And this is why if you think about bispectrum or trispectrum in cosmology, those estimated turn out to be quite noisy. So what is the insights of scattering a transform? So the key idea here is that, is it possible that I can capture the tail without taking super linear operation? And turns out that it's possible. In the 1D case, what you would do is to take the expectation of the distribution and then take a nonlinear operation. So you fold the distribution and then take the expectation and then fold the distribution. So you can iteratively fold the distribution. And through this way, you can capture the tail of the distribution without exploding the sampling noise. If you look at this operation, right, then you can start to see some resemblance between this and CNN, right? CNN is actually doing the same operation. You keep iterating between convolution, nonlinearity, and averaging. And it seems like a dark magic that this always works for different patterns, but the mathematics behind is quite deep. So the idea here is that the only way that you can capture higher order moment without exploding the variance is by taking this operation iteratively. And this is why you can build a ResNet 50 and you can still keep extracting information, because this is a folding processes that allow you to keep the information as much as possible. So if you believe this, then it means that it can be done by purely analytic operation, that you can try to capture as much information in a stable way. So if you look at the weak lensing case that I mentioned earlier, comparing the power spectrum and the scattering transform, the scattering transform actually outperform the power spectrum by a lot. In fact, if you look at the figure of merits for different future survey, DES, LSST, RW first, not only we are outperform the power spectrum by a lot, we are also performing on par with CNN. This means that we do not need to do deep learning. What we need to do is to understand what is the inductive biases in the deep learning and come up with a better analytic tool. So of course, I cannot resist myself to stop here, because all of this is just very generic. It can apply to basically everything in astronomy. So we also look into reionization. So with SKA mock, comparing the power spectrum with the scattering transform. Again, we show that the scattering transform outperform the power spectrum by a factor of 5. So with this, I just want to leave you with a summary, right? So we often take CNN as a black box. I don't think like that is the correct way to think about CNN. So a lot of very successful neural network like architecture come with deep understanding of the inductive biases, meaning that what are the symmetry that the network like try to extract. In the case of CNN, apart from the translation or invariance, what you try to do is actually make sure that you have like distortion like stable. And by simply including that like symmetry, you can actually get quite a lot more. And this is really simple. So the code that we use is 20 lines of code, and I can convince you that it outperforms basically every heuristic out there. So with this, I will stop and take any question that you might have.
Okay, thank you a lot for the really nice talk. Are there any questions from the audience? Okay, I think that I have one.
Sure.
Is about the iterative process that you were mentioning between comparing the outliers with the expected value. When we do this kind of operation, should be worried about something, or we can do in any case? I mean, are there any requirements to do such a procedure?
Yeah. So if the goal is to just do a parameter like estimation, then there's no like limitation. So what you like really do is try to just decomposing map in some smart way. But one of the key limitation here is that because you take the modulus of the field, and this really breaks quite a lot of things if you try to analytically like derive what is the evolution of the mode, because it's really hard to come up. So the very amazing thing about the modulus is that if you expand that out, you are capturing very higher order like moment. But also it breaks the the linearity. So this make, if you want to evolve, the modes of the scattering like a coefficient as a function of the cosmological time, it will be almost impossible. This is the gain that you capture more information, but you lose the fact that you are quickly capturing the nonlinear feature, meaning that you cannot build like a perturbation, like a theory from that.
Okay.
So if I may to follow up on that, so it's the difference between the scattering transform method and the traditional CNN is you just predefine the neurons instead of using like a relative function or predefine.
Right.
Like
so you predefine the convolution, and there are some smart choices. They are very generic like choices that you can use. So you are still doing convolution, modulus, and take expectation. The point here is that most of the images that we carry in astronomy is really simple, so you do not need to fine tune the convolution kernel. So all the deep learning that you are doing, you are just fine tuning. But there's no reason to fine tune because these maps are so much like simpler than a rabbit.
Yeah.
Right.
Yeah. Okay. I think we are quite on time. We can take a 15-minute break and come back at 6:10 UTC. So that's 15 minutes after now. See you later, guys.
See you later.
I think I will just stay here. I don't know if I quit, whether the YouTube live thing would be cancelled or not.
Yeah,
So
it's better to stay here.
Yeah. Okay, it's about time, right?
Yes, in 1 minute.
Yep.
We should restart.
Yeah, well, I think Humi can start sharing his slides. Humi, are you there?
Yes, yes, I am here. Okay. I will. Can you hear me?
Yep. Nice background.
Share.
Okay. So,
do you see my screen now?
Yeah, it works. It works. Perfect. So our next speaker is Mr. Hilmi. He's a PhD student at the University of Melbourne. And whenever you're ready, you can start.
Okay. Thank you. Good afternoon, good morning, and good evening, everyone. So my name is Hilmi. I'm a second-year PhD student from the University of Melbourne. I work with Michele and Nicha, and today I will give a talk about my recent work, which thanks to the coronavirus has been done fully online. So the title is Contamination of Lyman-Brick Galaxies at redshift 8 in the Hubble data, correlation with redshift 2 Lyman-Brick Galaxies. And this is the outline of my talk today. So first, I will give a very quick introduction, and I will continue with the two part of analysis. The first one is about the correlation of the number counts, and the second part is the angular correlation function. And for each of the analysis, I will explain the data set because we use a different data set, and I will close my talk with summary. So just a very quick introduction here. I'm sure everyone already know that this is the cosmic history of our universe, and we have the IGM was neutral and now ionized. So we know that we call that as cosmic ionization, and the star-forming galaxies at high redshift are prominent candidate sources for producing the cosmic ionization. And high redshift galaxies, high-redshift galaxies are basically identified either from the Lyman alpha emitter or the Lyman alpha emission, or from the spectral break in their narrow in their broadband photometry, as we call it Lyman break galaxies. And Lyman break galaxies at redshift 8 will have the Lyman break redshifted to 1.1 micron, while the Balmer break at redshift 2 will have the Balmer break redshifted to 1.2 micron. And therefore, both of the break, different break, but yeah, both of the break of those two type of galaxies will enter the same broadband of the Hubble infrared camera, and Balmer break galaxies at redshift 2 might be misidentify as Lyman break galaxies at redshift 8 and contaminate the sample. And we want to study this contamination coming from foreground galaxies of redshift 2 galaxies on the redshift 8 galaxies. So the first part of analysis, we will discuss about the correlation of the number counts. And here we use the data from the brightness of reionizing galaxies, or BORG, which is actually a Hubble survey focusing on finding Lyman-Brick galaxies at bright Lyman-Brick galaxies at high redshift. And it consists about 70 random independent pointing with limiting magnitude varies between 25.6 to 27.5. And catalog of Z2, there are two catalogs, Z2 and Z8, and the catalog of Z2 is provided by Cameron 2019, which consists of 490 galaxies, and the catalog of Z8 is taken from Bradley 2012 and Smith 2014, which consists of only 42 galaxies. And so the galaxies at redshift 2 and redshift 8 are physically uncorrelated. So we expect there is no, basically they are uncorrelated, but if some of Z2 galaxies are detected as Z8 galaxies, we expect that their number counts will be somewhat correlated. And so as we can see in the picture on the right side, this is just illustration. Yes, so there are about 69 fields in the BORG galaxies, and if there are contamination, we expect that there are correlation, because some part of the number count of some part of Z8 galaxies actually are coming from Z2. And if there is no correlation or there is no contamination, then we expect that there is no correlation, and we want to study how this correlation of the number cones is changing over the number of possible contaminant. And we will explain that later. So, but before that, we also need to take into account the number cone of faint Z2 galaxies, that is the galaxies fainter than 24.5, or the galaxies within the red area in the right plot, because the galaxies is not included in the Cameron sample, which Cameron sample limiting magnitude is somewhere around 24. But the Borg galaxy, the Borg Z8 galaxies is taken with the limiting magnitude from 25.6 to 27, around 27. So there we know that there are some part of faint Z2 galaxies that might not be included in the Cameron sample, but contaminate the redshift 8 galaxies. And so we use the luminosity function to estimate the number cone of faint Z2 galaxies, that is the number cone representing in the red area, and also intrinsic number cone of Z8 galaxies here. And before coming to our Monte Carlo simulation, I want to explain about the leakage fraction. We introduce a leakage fraction here to simulate how many of faint Z2 galaxies will be detected as Z8 galaxies. So we are already familiar with the contamination fraction. Basically, it is the number of contaminant per the redshift 8 galaxies. And here we introduce a leakage fraction. Basically, it is the number of contaminant per the number of faint Z2 galaxies. And you can see 3 panels here. On the left one, the red one is real Z8 galaxies, and the blue one is Z2 galaxies, and the yellow one is actually a Z2 galaxies, which is detected as Z8 galaxies. And therefore, for the left panel, the leakage fraction is 1/7, and the contamination fraction is 50%. For the middle one, then 100% contamination, because what we actually observe as Z8 galaxies is actually Z2 galaxies. And for the left one, if there is no leakage from Z2 coming from Z2 galaxies, then of course contamination fraction will also be 0 here. And we want to simulate. So we are conducting the Monte Carlo simulation here by like trying from leakage fraction 0 until 10%. And for each value of leakage fraction, from leakage fraction 0, for example, we generate a Poisson number count of Z2 galaxies and the number count of Z8 galaxies. Because we already estimate that from luminosity function, then we can generate a random Poisson number here. And from Z2 number count of Z2 faint galaxies and the leakage fraction, we can derive a number of contaminants. And from number of contaminants to number of Z8, basically we can derive the number of observed Z8 sample, and from that and to with the number count of Z2 from catalog, we can calculate the percent correlation coefficient, or CP, here for each leakage value. And we repeat that thing for 100 times for each leakage fraction value. So we will have something like this. So the horizontal line here basically is just percent correlation coefficient estimated based on the catalog, on the real data. And we have, obviously, we will have the percent correlation coefficient is 0 if there is no correlation, and 1 if there is a positive correlation. And when leakage fraction increase, obviously the percent correlation coefficient will also increase, because the number of the number of contaminant will increase, and indicating that the Z2 and Z8 galaxies will have stronger correlation, of the number count will have a stronger correlation. And the right panel is contamination fraction as a function of leakage fraction. We can also derive that from the luminosity function, which shown by line, and also by Monte Carlo simulation function, Monte Carlo simulation, which indicated by red square and the error bar value, error bar here. So the blue dot is like 100 times simulation for each value of leakage fraction. And that is, we also, in addition to this, we also conduct a Monte Carlo simulation while assuming the limiting magnitude of 26.8 for all field, because all the 69 Borg field have different limiting magnitude, but here we are assume a same limiting magnitude for 20 or the field that is 26.8 is actually the median of limiting magnitude. And here we see that the percent correlation coefficient is 0 when the leakage fraction is 0, because the leakage fraction 0 means no contamination, and there should be no correlation between G2 and G8 galaxies, and the leakage fraction versus contamination fraction is actually similar to the previous one. However, if we assume limiting magnitude deeper, like for example, like 28, then we notice that for the contamination fraction and leakage fraction versus leakage fraction, here the contamination fraction much lower, or we can show in the next picture here, like all of in the same plot. We can see that when limiting magnitude is deeper for all of field, then we will see that for the same value of leakage fraction, the contamination fraction is lower, because we will get more G8 galaxies when we deeper limiting magnitude, and contaminants, however, is following the limiting luminosity function of G2 galaxies, not G8 galaxies, and they evolve slowly the number count of G2 galaxies, and therefore we will notice that contamination fraction will be lower for the same value of leakage fraction if we go deeper in the limiting magnitude of survey area here. And so we try to derive the percent correlation, the leakage fraction value, by taking into account all of the data point which fall into the 1 sigma uncertainty of this red area, the percent correlation coefficient, which based on the observation, and our estimate is 32% of the contamination fraction, which actually lower than the contamination fraction from Bradley et al. And they estimate from based on scattering photometry, but our estimate, so the method is different, and we notice a difference here. But yeah, our estimate here is we weight every data point within the red area equally, while we actually consider the distance to the red horizontal line here. I actually want to move the cursor, but I could not see the cursor here. Okay. So the second part is spatial correlation or angular correlation function here. And so for this part, we use the data set from candles, and we use the photometric catalog from Merlin, which consists of 7,000 redshift 2 galaxies and around 90 redshift 8 galaxies. And as you can see in the right panel, that is the distribution of all the photometric galaxies in this catalog. And for the next slide, for the next explanation, I will, how to say, good sort. When I say good sort, it is basically all of the field excluding the XDF here, and the XDF is that the smaller field but deeper, because we have to conduct the analysis separately. And to quantitatively analyze the spatial correlation, we use the angular correlation function, which basically defined as the probability of finding 2 galaxies with an angular separation theta. And to measure this omega theta, we need to count the pair of galaxies as a function of separation theta here, and we use the KD3 here and divide by the expected counts for the random distribution. So we generate a lot of random distribution here, and we use the Landis-Sale estimator, which we can see here, like omega is DD minus 2 DR plus RR divided by RR. And the measurement of omega theta are underestimated by an additive factor known as integral constraint. So our result that I will show you later actually is omega observed, not omega true. I just want to mention that. So we first we want to see the angular correlation function for G2 galaxies, and for each G2 galaxies and G8 galaxies, and we will continue to the cross correlation between these two. And this is the distribution of G2 galaxies in the XDF field on the middle and the good sort field on the right. And the angular correlation function showing indicated in the left panel. The red one is taken from good sort, like on the small scale, like we see like
sorry, 1 minute left.
Okay, sorry, I will go through then. Okay, so for the Z2 galaxies, we see the clustering on the smaller scale, and that is also the average on the right side. And for Z8 galaxies, we don't see any special here. And for the cross correlation, is actually just modified from the previous equation, but here we use D1, D2 instead D, and D1, R2 instead DR, and you can see from the equation itself. And yeah, in the good sort, we see on the small scale here, we can observe there is a kind of correlation axis here, which possibly indicating that some contamination might exist. And for XDF, it is like this. And yeah, if we try to average the cross correlation between Z2 and Z8 galaxies, and yeah, the smaller scale here, we still see the special correlation axis in good sort. And so I will close with the summary. So the goal is to study the contamination of Z8 galaxies by analyzing the correlation with redshift 2 Balmer big galaxies. And we have the data from Borg sample and also from candles have a legacy field. And for the method, for the Borg sample, we use the Monte Carlo simulation. And for the spatial correlation, we use the cross correlation function. And we find out that we found that with DV limiting magnitude, contamination will be lower for the same amount of leakage. So if we can, have a deep limiting magnitude, then we are very sure that the contamination fraction will be lower, even though we have some amount of leakage from Z2 galaxies. And yeah, we also find that probably in the good sort, some special correlation exists, and it might pointing to indicating a kind of contamination in the survey. I think that's all. Thank you for listening. So if any question.
Yeah, I think there's already a question in the Slack channel, and unfortunately we run a little bit late, so perhaps we need to move on to the next speaker.
Okay, thank you.
Okay. Next we have Ela Krinking, talking about the first measurement of quasar lifetime distribution.
Thanks. Let me share my screen.
Yeah.
Okay. Thank you very much for this opportunity. I want to present our recent work on estimating the quasar lifetime distribution. So I guess I need to start because I see people doing very different stuff here. So I need to give it very short but general introduction. So the quasar lifetime is the duration of the accretion episode on the supermassive black hole that power quasars. And so it's obviously important to know this time scale if we want to estimate how the supermassive black holes gain their mass, which now detected up to 1 billion solar masses already at redshift 7, when the universe was just less than 1 billion years old. So there are a lot of methods that were trying to address this issue and trying to estimate the quasar lifetimes. There is a nice plot from Christina Eiler's paper from last year that tries to summarize our current understanding what's the value of this time scale. So all these different points, they come from different methods, but one of the most popular ones, I would say, is to look at so-called quasar proximity zones, the regions of highly ionized material around quasars. And so usually people were looking at these proximity zones in the H1 Lyman alpha line of the quasar spectrum. And usually it was done at redshift 3 to 4, but we instead work with helium-2 proximity zones. So it's the same analogous proximity zones, but just in the helium-2 absorption line. So this slide just gives you a brief summary how the proximity zone look like in well, in theory, which is the top cartoonish plot, and obviously it depends on the duration of the accretion. So the longer quasar absorbs material, the longer it shines the radiation away, and thus ionizing the bigger zone around itself. So the bottom left panel shows the example of the helium-2 proximity zones in the spectra of quasars that we have. So unfortunately, we have only 22 quasars in our sample, but this is due to the fact that to get the spectra, you need to go to ultraviolet because of the helium-2 absorption transmission. And so it is possible only with HEST, and all these quasars are extremely faint. But anyway, so the right bottom plot shows you the compilation of all the proximity zone sizes that we measured, and the error bars here are basically the uncertainty in the determination of the redshift of the quasar. Here I need to make a small comment that what we and actually everyone is measuring from the individual quasar proximity zones is not exactly the quasar lifetime, but the quasar, what we call quasar on time. Simply because when you observe the quasar, it doesn't mean that it will stop shining exactly at that moment. The accretion episode can continue in the future and stop at some point in the future. So you measure effectively the lower limit on the quasar lifetime. Okay, so how do we get from observed proximity zone sizes to actual estimate on the on times or lifetimes? To do that, we use the combination of hydrodynamical simulations from which I extract the realistic density, velocity, and temperature fields in the form of one-dimensional skewers. And then I have the custom 1D radiative transfer, where in each of this realization of the density, in the beginning of the sightline, I put the quasar with some parameters, and I propagate radiation through this media, and I get some plots like this on the right side. This animation shows you how the size of the proximity zone, basically in the spectrum, depend on the quasar lifetime in the model. So there are three parameters. The main parameters that models depend on: the quasar on time or lifetime, the helium to ionizing background, which just mimics the ionizing photons that are coming from the sources, other sources in the universe. And it also sets what we call the initial helium-2 fraction. So it's the helium-2 fraction in the universe, basically, around quasar before quasar accretion starts. And the third parameter is quasar luminosity, but it is fixed from the observations. And so doing these simulations, we end up with a grid of models for each quasar in our sample, something about 400 models, depending on the parameter values. And each model basically gives you a distribution of the proximity zone sizes as shown on this plot on the left, which has in it the uncertainty in the redshift as well. So it's this nice distribution. And if we measure the mean and the standard deviation, these distributions, we can make these animations that show you how the size of the proximity zone depends on the lifetime, which is the top plot, and on the initial helium-2 fraction. So obviously, we are mostly interested in the top top dependence shown in the top plot, but the bottom one is also important. Also because we don't really know from observations what the exact helium-2 fraction in the IGM at this redshift. So we need to effectively marginalize out this uncertainty. And so we create a grid of likelihood values based on these distributions, right? Because for each quasar, we know the size of the proximity zone, which is shown here by the dashed blue line. And if we evaluate this PDF at the value of the observed size of the proximity zone, we get the likelihood for this model. So we do this, and then we run the MCMC algorithm on these likelihoods. And these are the results for individual quasars in our sample. The left plot shows you the marginalized posterior distributions for the quasar on time. And the right one illustrates the size of the proximity zones that we observe and the corresponding quasar on times. So the limits upper and lower limits here are basically due to the redshift uncertainty. If it's very big, then you get something like that. This procedure is in the top left panel, where you cannot really say, place the mean and 1 sigma. Anyway, so the distribution of the inferred dawn times from these 22 quasars is surprisingly broad, and well, we didn't really know when we saw it what's the underlying distribution of quasar lifetimes from which it was drawn. And so to do that, we actually use the same set of hydra and radiative transfer simulations, but it's slightly different, or not slightly, actually completely different statistical approach. So first of all, we assume that the underlying distribution of the quasar lifetimes has the log normal distribution. It's a simple assumption, which is given by this equation in the middle, in the top. And what we want is to infer the parameters of this distribution, the mean and the sigma. So we create a grid of values for the mean and sigma, and then do the following thing. So here's an example distribution of lifetimes in this plot. So first I will describe it from the position of the MCMC algorithm. So MCMC proposes the parameters of this distribution, the mean and sigma. Given these parameters, we draw, well, MCMC draws the samples from this distribution, samples of the quasar lifetime. And then we know that the connection between the quasar on time and the lifetime, which is simply a uniform distribution, right? So we convert all these values to the actual quasar on times. Then also we use the Fred Davis's helium-2 reionization model that delivers the helium-2 fraction at each redshift where we have our quasar. And so for each T-on, we find the corresponding helium-2 fraction at this redshift. Then we go to our simulations, and for each of these pair of parameters, we find the corresponding distribution of the proximity zone sizes in our simulations. We also interpolate between our grid points at this point. And then from each of these, so at this point, we can have something like 10,000 combinations of T-on and X helium-2, depend on, I don't really remember how many we had in the end. But anyway, so for each of these parameters, for each of these parameters, we find the proximity zone distribution. We draw proximity zone sizes from this distribution and combine them in this huge joint distribution of the proximity zone sizes, which we fit with kernel density estimator. And in a similar fashion than before, we evaluate this density at the size of the observed proximity zone for this quasar, for the quasar in question. And so we repeat this for all the grid points in the quasar lifetime distribution grid. So we have something like 1,000 likelihood values per quasar. And then finally, we do we multiply these likelihoods to get the joint likelihood of all our entire sample, and run the MCMC on this joint likelihood. So these are the results. The top plot shows you the MCMC 2D contours and 1D posteriors for the mean and the sigma of the quasar lifetime distribution. And the right panel shows you the just randomly chosen 100 realizations of the posterior and the maximum likelihood one. So this is the first determination of quasar lifetime distribution. And so first of all, it also kind of points to the fact, if you remember the first plot that I showed was different measurements of the quasar lifetime, although there was a broad distribution, but there was some band around 10 to the 6 million years, around 1 million years. So our analysis also kind of points towards this value roughly, and which is very, well, it's not bad, but it's really hard to grow the massive black holes at high redshifts if you accrete only for such a short time scale. But so nobody knows yet why is it so, and what's the solution. But anyway, we also know in this distribution we found the nice analytical formula to infer the probability of finding the so-called young quasars that are reported by Christina Ehlers and others at redshift 6, 7-ish. So these are quasars that, from the size of the proximity zones, it just happens that their lifetime should be less than 100,000 years. And they report, based on their observations, that the fraction of such young quasars is about 10%, although I should say that most probably their sample is not complete, so I would say that this number will be higher. Anyway, so based on our lifetime distribution, we can actually also estimate what this fraction should be. And we find some values that are actually consistent with that determination. Right, so it's everything that I wanted to tell you now, and if you have any questions, I'm happy to answer, and yeah, thanks.
Thank you, Ela. Do we have questions? I put one in the Slack channel. I was just wondering if you can comment on the accuracy of the lifetime information using helium-2 for low redshift quasars compared to the information for quasars at high redshift using the hydrogen proximity zone.
That's a good question. So first of all, where is this plot? So when you try to infer the individual on times, right, like we try to do here, you really need precise measurements of the quasar redshifts, because so the top panel here, right, where the uncertainty in the redshift estimation is something like 600 kilometers per second. So obviously your posteriors now here, they at most they will give you some limits on the estimate, whereas here the uncertainty is less than 300 kilometers per second. You have this nice posteriors. For high, so big, our sample lacks the precise redshift estimates because of the various reasons. And the hydrogen proximity zones at higher redshifts, around 6 or 7, they have very nice redshift estimates coming from ALMA, for example. I mean, they basically have more lines that we lack in our spectra to estimate the redshift. But if you then try to infer the quasar lifetime distribution, we actually found that the redshift uncertainty is not that important in this case, just because it is swamped by all this statistical stochasticity and the relationship between the quasar lifetime and the on time, and also the uncertainty in the helium-2 fraction. So it actually all this relationship, they actually make it possible to use samples with poorly estimated redshifts.
Yeah. Okay. Thanks.
Thank you.
Okay, I'm not seeing any more questions, and I think we can move on to our next speaker. So next we have Yihang Zhou talking about the to understand the impact of semi-numerical reionization using CNN. So this is another machine learning talk.
Okay, hello everyone. I'm Yihang Zhou. I'm very happy to give this talk here. I'm an undergraduate student from San Diego University. The topic of my talk today is to understand the impact of semi-numerical models when using CNNs. I will start with some background and motivation. As some presentations mentioned before, the machine learning has been used in many words as an alternative method to interpret the 21 centimeter signal, since machine learning could take advantages of all the information included in the data, while some traditional way like power spectrum is only sensitive to the Gaussian information. So I list some words here. They are machine learning words in this field. Some of them are I use machine learning to use parameter estimation, and some are to rebuild the underlying density field from the 21 centimeter signal. And also machine learning has some great potential in this field. Some problems are still remained. One of them is whether the machine learning has some model dependency. To make sure we could use machine learning in the upcoming 21 centimeter observation data, we want to build robust networks. We want it insensitive to the underlying models. So in this work, we work on in the context of regressing the CMB optical depth from 21 centimeter snapshots, and we compare the CM behaviors on the two reionization models, 21 cm fast and 0 ion. We want to see if the CNs has some dependencies on the underlying models. And I will first give a brief introduction of the models we use in this work, 0 ion and 21 cm fast. 0 ion treats the redshift reionization field as a biased version of overdensity field, because we know we believe these two fields are highly correlated with each other. And 0 ion give biased expressions for the reionization field, and this is where the free parameters come from. And the density field 0 ion used is M-body simulation. On the other hand, 21 cm fast includes much more direct physical reionization process, so it has much more astrophysics parameters, and it uses the 2LPD density field. Here is some information about the data set we used. We picked 30 redshift. We picked 30 different redshifts, and at each redshift, the slices is 512 square, corresponding to the 2 giga per sec commoving distance. And what's more, we include the instrumental effects. Here we use the HERA design parameters. First, we consider the maximum angular resolution, and we also consider the wedge filters. So it's like we remove all the Fourier modes in the wedge filters, and the largest resolution limit to be 0. And also we remove the mean value, so it's like we just use a fluctuation of the data. Here we list the parameter space we use to generate the samples. And here we give the example of data, of training data. The upper two is the original snapshots, and the bottom is the snapshots with the instrumental effects. From the upper two, we can see the 0 ion has much larger variation because it has some yellow dots here, right? And they are very similar to the naked eye, but it turns out they are very different to the networks. And here are the results of our training. The basic idea is we train the models on one reionization models, and after we achieve the good results on one of the models, we predict the tau on both of them. In the ideal case, the networks could be insensitive to the specific details of one model, so they could achieve good results on both of them. But it turns out it's not true. When the models trained on 21 cm fast, the results on 0 ion has large bias, and vice versa. If we want to achieve models that could achieve networks that get good results on both of these models, we must include the data data from the two models in the training data set is what I showed in the right column. We can see that the prediction of the two models are both within 5% error. And another result we find is 21 cm fast is easier for the networks to train compared with 0 ion. We can see that from the architecture of the networks and the loss function. I show the architectures here we can see that once a network is trained on 21cm fast, it has a much simple architecture. It has fewer convolution layers, but it could achieve as good results as the other two. And for the loss function, we can see once the network is trained on the mixed data set, although the model is trained on the two data sets simultaneously, but the loss is dropped faster for 21cm fast, it could achieve good results with fewer epochs. And another interesting result we find is the data at low redshift is much more important for the network to make the decision. For these plots, we replace some slices in the snapshots. Here we first pick 5 21cm fast snapshots, and we replace the Jensen-6 slice with corresponding serial snapshots. The snapshots here we use that also share very similar reionization history, and the red dashed lines are the prediction results of the original 21cm fast snapshots, so it's like the original results. And the black dashed line is the prediction results for the Orion, so it's like target results. Once the swapped snapshots has a prediction close to the black dash line, it means the redshift is more important. And when the result is close to the red dash line, it means the redshift doesn't play an important role for the networks. And so in these plots, we can say the low redshift is more important. And on the right columns, it's networks trained exclusively on the red and low on the high and low redshift data. It could say that once the network is trained exclusively on low redshift data, the results we achieved here is very similar to the networks we trained on the whole redshift range. So we can say the networks mainly use the data at a low redshift. And here is the Monte Carlo dropout results. It is used to give an estimation of the uncertainty. And we also investigate the model dependency on the cosmology data. For the training data set, we didn't vary the cosmology parameters. We just use different astrophysics parameters. And in these plots, we can say that once we use different cosmology parameters, the networks also still outputs similar results. So we can say our networks pay less attention to the cosmology parameters. And here is the conclusion. I will stop here. Any comments and questions are welcome.
Okay, thank you. That was a very nice talk. Maybe I can start with some of mine. I was wondering, like, when you were generating the training set, did you use the same density field? Because that's basically the initial condition for the output.
What do you mean by using the density field? Of course, we will use. You mean the? You okay. Mean
like for 21cm fast, you need an input of the density initial density field, so that you can generate the 21cm signal from that.
Yes, we use a QLPT density field.
Okay, it's and you keep like version. Initial. Okay. Okay. I like when I was looking at your prediction in one of the slides, you showed like when you train the network using 21cm fast and make predictions using the other model, and then you do the other way around. I see it like if like in the middle panel, for example, this one you see a S shape in the middle panel for the orange curve, but it's like pretty monotonic, pretty straight for the case in the left. I was wondering if you take a time to look into this.
The behavior on the other model, I mean the model which is not included in the training data set, since the behavior on it is different from round by round. So So
Okay. But it looks like for all the low tau models, you are under predicting the value using the real, but for all the high one, you are over predicting it.
You mean the mid data set?
No, I mean the middle point.
Yes, I mean the behavior on the 21 cm fast in this case is different from round by round. If we change the architecture, for example, the behavior of 21 cm fast may be like maybe similar to this case. So I don't think we could say we can get some conclusion on the behavior of the other model.
Okay, thanks. Is there any other questions? Okay, if not, let's move on to our next talk. So,
okay, our next speaker will be Balu Sridhar, a PhD student from the University of Melbourne, and he will talk about the application of Monte Carlo augmentation to embodied simulation.
And
okay, now we'll start with, yeah, perfect.
All right, all good. Can I start then?
Yeah, you can start.
Okay, yeah. Hi everyone, my name is Balu Sridhar. I'm a second year PhD student here at the University of Melbourne. I work with Professor Stuart White and Dr. Bradley Gray, as well as Simon Mutch. And I've been extending a work by a former PhD student of Stuart, Yisheng Chu, who's now doing his postdoc back in China. And Yusheng Ting is also a member of the team. So I've been talking to you about the Monte Carlo augmentation of some embodied simulations. So I've been using a couple of embodied simulations, and they are maintained mostly by people from Western Australia, particularly Professor Chris Power from the University of Western Australia. So we have a semi-elliptical model, which we call the Meraxes model. And what makes Meraxes interesting, particularly for the EoR community, is that it is actually coupled with 21 centimeter fast. So that there is feedback both between the galaxy formation part of Meraxes as well as the EoR modified 21 centimeter fast of Meraxes. So yeah, and the simulations which I've been using, they are all dark matter only embodied simulations, and they are called the Genesis suite of simulations. They are tailor-made for EoR studies. And in particular, the box I've been making use of is this box, which is the L210 EN4000 box. So that's a 210/8 megaparsec box, and this is a particle mass of a one dark matter particle. And when I said that it's tailor-made for EoR, what I meant is that we have almost 120 snapshots between the redshift 30 and 5, which are equally spaced in time. So the cadence of the simulation is almost 11 million years. And on the right-hand side, you can see the halo mass function from the box. What I want you to notice from this figure is the mass of the smallest halo, which we are able to resolve. So that's a few times 10 to the power 8 1/8 solar masses. And from now on, I will be referring to this box as Genesis box. And so this is the main plot. So the blue line here shows you the atomic cooling limit for the galaxies as a function of redshift, and the red dotted curve here shows you the mass resolution of this Genesis box. So what this implies is that when I'm doing the simulation, we are essentially losing out all the halos which are between this red line and this blue curve. So consequently, I'm missing out the effects of all the galaxies which are hosted by these halos on the EoR morphology, for example. So what we have done to compensate for this is, so this is a need for augmentation. For example, if you want to properly study EoR, you need a large volume because we are still limited to statistical studies of EoR, for example, like the power spectra, for example. So if you're simulating the power spectra, for example, for the power spectra to converge, you need a large enough volume. But if you keep the number of particles the same and you go for larger volumes or larger boxes, that actually leads to lower resolution, which you don't want, obviously. So you choose a big enough volume, and then you increase the number of particles. So that will actually give you a higher resolution, but that actually leads to more computationally expensive simulation, dark matter only n-body simulation. So we have introduced a code called dark forest. So that's for augmenting the halos. And I will be talking about n-body halos as well as MC halos. So when I refer to n-body halos, I'm actually talking about the halos which are already there in the n-body simulation. So that's the pure n-body halos which are already there. And the MC halos or Monte Carlo halos are the halos which are introduced by dark forest. So this is a small schematic of dark forest. And yeah, so there is a mass cut value. So for now, I don't want you to focus on the mass cut minimum and mass cut maximum. So for below a particular mass cut value, between mass resolution, which we can actually control, what the dark forest will do is it will remove all the n-body halos. So we essentially do lose out a few of the n-body halos, but that's actually a very small fraction. So and then the dark forest will introduce new MC halos into the box below the mass cut value, and above the mass cut value, all values will be n-body halos which are already there. And now instead of having a single mass cut value, dark forest actually have a range of mass cut values which goes from mass cut minimum to mass cut maximum. So below m-cut minima, everything will be MC halos, and above m-cut maximum, we'll only have the n-body halos. Between m-cut minima and m-cut maximum, we will actually have a hybrid population of both MC halos as well as n-body halos. And then yeah, so this is so the violet curve here, the dotted line here actually shows is the mass resolution of a new simulation, which we are calling Genesis Plus box. So Genesis Plus box is essentially the same volume as the Genesis box. So the Genesis Plus is what you get after you run dark forest on Genesis box. So this actually has a much better mass resolution. So that's actually tuned to be the same as the atomic Cooling limit at redshift 20. So now I theoretically have all the halos which are capable of hosting a galaxy down from redshift 20 to 5. So this Genesis Plus simulation is now effectively an n-body simulation of almost more than 1 trillion effective particles. And yeah, so and here I'm showing you the halo mass function from the Genesis and Genesis Plus. As you can see, in the Genesis Plus simulation, we are now able to sample much lower halo masses. And once you have a Genesis Plus simulation, what you do is you run the axis. And here I'm showing the stellar mass function. And in this one, I'm showing you the luminosity function. So if my aim was essentially to study the stellar mass function or the luminosity function, essentially the galaxy evolution, for example, we could have stopped here, because what you essentially need is a proper merger tree. But for EoR studies, it's not enough to have a number of halos in the box. It's also important that you also assign them proper locations. So dark forest actually properly assign locations for the newly assigned halos. So we actually have two different methods. One we call the sampling method, and one we call the evolving method. So the assigning and evolution of these positions for the newer halos actually goes backward in time. So we start from the lowest redshift, which is 5, and then we go backward in time. So at the lowest redshift, and for every redshift where a new MC halo essentially pops into existence, where it is not the progenitor of any other halo, what we do is we use a dark matter density field from the Genesis box, and then we make a halo density field, and then essentially we use this halo density field as a probability distribution, and we sample from this halo density field to assign locations for this MC halos. And in the next step, when the halo already exists, and for the next snapshot, we actually evolve it instead of doing the sampling method. So for that, we use a linear continuity equation. So we essentially use this equation. We again make two density fields at two adjacent snapshots, and we figure out the velocity field which we need so that these two density fields will, these two HERA density fields will essentially match. So for example, in this formula, if we take the Fourier transform, it's very easy to solve for the velocity field in the Fourier space. And then you do a second inverse Fourier transform to figure out the actual velocity to move the halos. And here is a 2-point correlation function. So if we compare the evolving method again with the sampling one. So for example, if you want, you can look at the sampling as a theoretically expected correlation function, which we should have. And the orangish curve as the 2-point correlation function of all the MC halos as well as the n-body halos in the box. And as you can see, they actually quite well match with each other. So this is actually essential if you are doing a proper EoR study and you want to explore the effects of these smaller halos on the EoR morphology, for example. And why am I doing this? So when Sheng did this similar work, we saw that there's a huge spread in the EoR history. So I've done the same for the Genesis Plus box. So the dark blue here shows you the EoR history for the whole entire box. And what I've done is I have essentially subdivided the big box into smaller subvolumes, 27 subvolumes, and their EoR history is shown in this light blue shade. So you see a spread. So this is essentially the same as a cosmic variance or a sample variance. So this will actually have an impact on the error predictions for 21 centimeter power spectra, for example. So that's what I'm actually trying to calculate. So here I'm showing you the EoR history difference between Genesis Plus as well as the Genesis simulation. As you expect, for the Genesis Plus simulation, we actually start reionizing much earlier by around redshift 20, because that's when the first galaxies start appearing in the box. And here I'm showing you the neutral hydrogen field. If you look closely, you will actually see that they actually look quite similar. I mean, especially on the larger scales. So the large scale structures are essentially similar between Genesis and Genesis Plus. But if you look closely at the top row, you will see that we actually have much smaller and finer details, and that's essentially coming in from these smaller halos. And here is the 21 centimeter sky average mean signal. And in the next one, I have varied the luminosity, the X-ray luminosity of the host galaxies. So and that also has a discernible observable difference for the EoR history. And here I'm showing you the mean signal when you vary the X-ray luminosity. So this actually makes sense. For example, if you look at the red curve here, that actually goes into emission for a long time. So that's essentially when I have 100 times the fiducial X-ray luminosity value. And so what this means is that the X-rays essentially heat up the cosmic gas. It is why we actually go into emission here. So I will just summarize here and leave it here. So what this has shown is that we need larger volumes and higher mass resolution. And having the ability to actually resolve these smaller halos actually have observed effects on the 21 centimeter signals. And I will be, my plan is to explore the effects of this one on the power spectra and the error covariance of the power spectra, for example. Yeah. So I'll just leave it here.
Okay, thank you. As usual, I'm asking to the audience if anyone has some question. Okay, while we are waiting, I have a question. I was wondering if in your simulation, did you account, especially looking for the reionization history, if you accounted only for stellar contribution, or if you have also the contribution of quasars?
Of what? Sorry?
Of quasars. Of black holes.
Yeah, we do actually. Yeah, we do. Yeah. So it's there. Yeah. So
okay.
you're asking me about the AGN contribution, right? Yeah, we do actually. Yeah. So Araxis does have AGN inbuilt, AGN feedback inbuilt. Yeah.
Okay, and also I wanted to ask if you can comment a bit more on the 21 centimeter signal that you obtain. In particular, in one of your simulation, you obtain one. The previous one. The Genesis. Yes, the green line. You obtain an absorption feature which is quite recent in Redshift because it's Redshift 10.
That's true. So I wouldn't read too much into the exact location. It's just that the amplitude changes as well as the location changes when you have more halos into this one. I wouldn't compare this to the actual experiments that are going on for example, like the Edges peak, for example.
Okay.
Yeah.
Okay, thank you. Okay, so I think that we can move to our last speaker of today, Shifan Zua. Okay, we can see your screen. Okay, so I leave the word to you, and so as usual, 15 minutes including questions, and yeah, that's it.
Okay. Thank you for giving me this chance. My name is Shifan Zuo, a postdoc in Tsinghua University. Today I will give a talk of interferometric array map deconvolution with neural networks. I will first briefly introduce the theory of radio interferometric imaging before my talk. As many of you know, due to the incomplete UV coverage, the image, actually the dirty image reconstructed by the 2D Fourier transform of the observability, which is observable of an interferometric array, actually is the clean image converted with a dirty beam, also called the PSF. Mathematically, the dirty image can be expressed as the clean image converted with the dirty beam, where the dirty beam is actually the shown as this, which is the Fourier transform of the sampling function. You see, actually the map, to get the clean image, we usually need to do an operation called the map deconvolution. You see the map deconvolution is actually a complex nonlinear operation. But fortunately, the forward process, we convert the sky map with a PSF is relatively easy to model. In recent years, the deep convolutional neural networks, the CNNs, has been widely applied for image processing, and we see the radio interferometric array map deconvolution is actually a typical image processing task. So in this work, we will use the neural networks for this interferometric map deconvolution. We have tried to use the autoencoder and the UNet, which are two types of CNNs for this interferometric array map deconvolution. We have used the maps reconstructed by the Tianai array as an example. The Tianai array is an interferometric array located in Xinjiang, China, which consists of 16 dishes and 3 cylinders. As you can see from this picture, this is the 16 dishes, and this is the 3 cylinders. And the dishes has a relatively small field of view, but the cylinders had a very wide field of view along these north-south directions. So it can actually make 4 sky maps. We have generated the simulated sky maps by using these two sub-arrays. Our sky models consist of two different components, the diffuse foregrounds and the 21 centimeter signals. This shows the sky, the top right two figures shows the sky maps reconstructed by the dish array and the cylinder array. And the bottom right two figures shows the PSF of these two sub-arrays. This slide shows the neural networks that we have used in this work. The left one is the autoencoder, and the center one is the UNet architecture. The difference between these two types of neural networks is that the UNet has an additional skip collections. But this neural network can only apply to planar images. For map deconvolution of the sky maps on celestial spheres, we use the techniques presented in Krochmanikov and Tomasi et al. To adapt the convolution onto this helix sphere. This uses structure of our neural networks. The neural networks are consist of 2D convolutional layers and makes Purning layers, and then use the ReRU activation function, and then followed by mixed Purning layers. We have generated 1,000 of data sets for training our neural networks. Among these, 600 of these data sets are used for training, and 300 are used for validation, and the left 100 for testing. This shows a sample of our generated data set. The left are the reconstructed image, and the right are the true sky images, which are the target of our neural networks. This shows the results we have got after the training of our neural network. This shows the result respectively for the autoencoder and the UNet, a general UNet neural network, and a deeper UNet neural network. And the right, for comparison, we have shown the true map in the right. So we see actually the autoencoder and the UNet neural network can both do very good work for the map deconvolution. But we also see that the UNet neural network can do much better than the autoencoders. We have then computed some quantitative measurements to quantify the performance of the neural networks. They are the mean square errors, which quantifies the total disagreement between the network predicted results and the true map, and the Pearson correlation coefficient, which is a measure of the linear correlation, and the peak signal to noise ratio, which quantifies the absolute difference of the pixel to pixel of the input and the predicted images. And then the structural similarity index measurement, actually which pays more attention to the similarity of the image structure, not just the pixel-to-pixel difference. The two tables shows the results of these quantitative measurements. We see the deeper unit 2 gives the best result of the deconvolution. Okay, let's give a summary of my work. We see that actually the reconstructed map of an interferometric array is a convolution of the true map with a dirty beam, also called the PSF. and we usually need to do a deconvolution to eliminate these PSF effects. Traditionally, we have used the Cockburn-Klein method to do this map deconvolution, but it works only well for point sources, not for extended sources. In this work, we have used the neural networks for this map deconvolution. I have tried 2 different neural networks, the autoencoder and the UNet, and we found that actually the UNet works best for the convolution of both the planar image in small field approximation and also the full sky map on the helix sphere. Okay, thank you. This is my work.
Okay, thank you, Stephen. Are there any questions?
I actually have one. So if you go back 1 slide to slide 11, I noted just 1 slide above your summary. Sorry, I mean slide 11.
Oh, okay.
Yes.
Okay.
Yeah, for the table, I noticed like 2 of the results have 100% accuracy, like the one on the bottom for the spherical result with the Pearson correlation coefficient. Like they are like, yeah. So this is it. I don't know. It is a bit concerning since you get like 100%. Or I'm misunderstanding the value in the table here.
Oh, actually, you see, because the array is located in the north hemisphere, some part of the sky map was not observed, so we have only compared the observable part of the sky, and then we have the correlation in this part. This part, the Pearson correlation efficiency is about 1.0, not exactly equal 1.0.
Okay, I might need to think more about it. Okay, thanks. Okay, is there any other questions? Okay. All right. If not, I think this is all we have for today. Our special session for our time zone. I'd like to thank all the speakers for their very nice presentation on behalf of the SOC. And personally, I'd like to thank everyone for joining us. We have a good number of participants, or at least in the middle. Now it's a bit late, especially for the east side. And we also had a pretty active discussion on Slack. So it definitely shows that we need a specific session for our time zone for future SAZERAC meeting. I trust everyone who has given a 2 AM or 3 AM talk will definitely agree with me. So finally, before closing the session, I'd like to encourage the speakers to upload their slides to the Google Drive and follow up on the question on the Slack channel if they haven't already done it. Okay, all the best, and see you next time.
Thank you. Goodbye, everyone.